Hi. So I can actually comment on the previous question, which is, well, two things. One, this is the system that we actually use to service when you're running the site. And the second is, even if you lose one piece of data, that actually affects a lot of things because there may be hundreds of pieces of content present to render a single page. So TAO is a system that stores and provides access to the social graph. So what is the social graph? The most obvious thing is the users and their friendships with each other. These are nodes and edges. But we put lots of other stuff in there as well. So as an example, let's take a simple post. There's a photo, somebody's made a comment on it, a few people have liked it. We can map this onto a typed node and typed edge graph system. We start with a node for the entire post. The photo is a separately managed entity, so it has its own node. Also, the comment is a separately managed entity, so it has its own node. We have some edges to establish ownership, so you can tell who's allowed to modify something. The likes turn into edges between users and the content. And then there's even more stuff. Even though this is a toy example, there's still a lot of nodes and edges. And I should point out that we use the social graph to encode not only the visible things, but also hidden implementation details. So for example, the EXIF data attached to a photo is probably stored in a separate node that's attached via an edge, because different photos have different types of EXIF data attached. So once we have this kind of flexible, it's a very powerful encoding, rendering the site turns into, we have some web servers. The web servers query the graph, they aggregate all the content, filter it, and then they emit the HTML. So an obvious question is, when do we actually do this aggregation and rendering? And to a first order approximation, we actually just do it every time. Every time we get a web request for this page, we're actually going to go to the graph, query the edges, query the nodes, filter them and aggregate them, and then present it to the user. The reason we do this dynamically is because, well, there's two reasons. One is Facebook is all about personalization. So the content that you're going to look at on the site is very hard to predict ahead of time. And it's different for every user. Every user sees a different subset of the graph. And it's also because of timeliness. So Facebook is a communications mechanism. So when somebody clicks like on your post, they're sending you a message. It's a very low friction message, but we want to show that to you as soon as possible. So by dynamically rendering every time, we guarantee that we get all the right content, all the freshest content. So TAO is the system that basically tries to handle the right side of this graph. So it includes, or as it's described in the paper, it includes the databases, cache machines, a communication stack in the web servers that lets you find talk to whatever server is supposed to actually answer your request. The dynamic nature of re-rendering from the graph every time means that the graph, the TAO system is essentially the highest layer that we cache aggressively. We cache the individual nodes and edges. And this means that the query volume of requests coming into TAO is very high. We have more than 1 billion queries per second, even during the slow hours. And we have a single deployed instance across all of Facebook, across all of our data centers, that provides access to the whole graph. So this is many petabytes of data in every data center. So what are the kind of what's the shape of the problem that we're actually trying to solve, or what are the limitations on it? Obviously, the first level one is scale. So if you're doing 1 billion queries per second and across many petabytes of data, you have to scale your system to a pretty large level. But more than just scale, we need efficiency at scale, because if each individual machine can't handle very many QPS, then we're going to spend too much money on it, and we can't actually build it and provide content. Or you can flip that around and you can say, the more efficient we make it, the better we can make Facebook, because we can have more rich content. The next constraint actually comes from the way that we resolve data dependencies. So TAO provides a very simple API. We don't have a please fetch this thing, then go fetch that thing, multi-hop query system, which means we do dynamic resolution of our data dependencies. So the web server that's actually rendering the post is going to start with the original node, and then it's going to execute a set of queries to navigate out. It can do those all in parallel, but we need more than one round in order to finish. So in this case, so in this toy example, we have 3 rounds. In a real example, it could easily be a dozen or more. And this means that we have pretty tight constraints on our read latency. In particular, we can't actually go from one data center to another on each of these query rounds, or we won't get the whole request done in time. So we have to be able to always read from a local data center. We also have timeliness. Like as I mentioned, it's a communications mechanism. And there's a second form of timeliness that we use, which is it's hard for our application programmers to work if they don't have read what you wrote consistency. So in a particular data center for a particular web server, if that web server has written something and then it goes and tries to do a read, we want it to be able to see that read. And finally, the same read amplification effect that causes TAO's very high query load means that we need high read availability. Because if you're doing, it's not uncommon to do 100 TAO queries to render a single Facebook page. So however many 9s TAO has, you lose the rightmost 2 of those for whether or not you're going to be able to render the page. So I mentioned it provides, TAO provides a very simple API. So this API actually predates TAO. It was originally developed as a PHP abstraction, a bunch of code that we called the Objects and Associations API that kind of wrapped around access to MySQL and then cached nodes and edge lists in Memcache. And this became very popular and became kind of the de facto way to access the graph in Facebook. So TAO basically replaces all that code with a thin communication stack and then provides the same API as a service. And we can do a better job because we can have a graph-aware cache and we can move the control logic into the caches. We don't have a look-aside cache. So the model is, we call it objects and associations, but objects are just nodes and associations are just edges. The objects they're identified by globally unique 64-bit IDs. So you don't have to know what the type of a node is in order to be able to find it. Like once you look up the object, then the type gives you a schema, but the ID stands alone. And then associations are just identified by a source node and a destination node and an edge type, or if you want to be pedantic, by the source ID and the destination ID. So there can be at most one edge of a particular type between any 2 nodes. As an example, I can only like something once. If we have a bidirectional association, then we just make edges in both directions, and we store those twice in the back end. And if we update the data on one, we update the data on the other. So if you look at the edges that come out of a particular node, so something that's identified by an ID1 and a type, there's often a natural ordering of these. In the case of the social graph, this ordering is almost always time. Like you're interested in whatever it is that was done most recently, the 50 most recent posts, or the most recent place that you checked in, or something like that. So we actually kind of bake this into the API by defining that every edge has a time, and then all of the queries that can access more than one edge in the system are defined over an ordered list of edges in decreasing order by time. We call these association lists. You can also get the size of the association list. So associations, objects, and association lists are the only things you can actually query using the Objects and Associations API. I should mention that time is actually just a 32-bit value. You can put whatever you want there, but it usually actually is a real time. These are it's not that important exactly what the numbers are on here, except for the very top level. In order to understand TAO's architecture, what you need to know is that we have 500 reads for every write. So we're basically, we can tolerate high write latency, but not high read latency. Everything is focused around making it so the reads work well. So let's go back to our top level challenges. We have efficiency at scale and low read latency. So how do we get that? So starting maybe 60,000 feet out or something, we get efficiency at scale by separating into different pieces that can be sized and scaled independently. So we have the web servers at the top, which are stateless. They're the most common type of we have more of those than we do of the lower levels. We have a cache layer, which is where we actually store all the objects and association lists. This is sharded by the ID, so every particular object or association list lives on a single cache box. And then we have a database at the bottom that's also sharded. The database is MySQL. We basically can scale the read capacity of the system by adding more cache machines, and we scale the storage and write capacity of the system by adding more database machines. So obviously there's some interplay, because if you don't have enough cache machines, then your hit rate goes down. And databases can also do reads. But basically, we have two big knobs that we can use to move ourselves to a point that's optimal. And this also adds improvements in our operational efficiency because we can have a separate people that are expert in databases and in the cache. So the simple kind of horizontal scale out starts to hit some bottlenecks when you get to the size of a data center or a set of buildings that are all coupled together. At the top layer, we have inefficient failure detection because if you have basically every web server is trying to discover failures in the cache server independently. So the number of failures that are, the number of errors that are required to actually discover failure gets larger as the top level gets bigger. Also, even though servers may be in the same building, they're not actually, the cost of going nearby in the building and the cost of going far in the building is not the same. The switches that are actually cost effective only have a limited number of ports, so you start to have inefficient usage there. We also start to have problems at the cache layer with, as our shards get smaller and smaller, the number of hotspots we get gets larger and larger. So we tackle both of these problems by subdividing inside a single data center. We have a subset of web servers talking to a subset of the cache, where the cache is complete in the sense that every ID maps to some element of the cache, but it's a distinct separate cache from the other ones. Obviously, this is going to have some problems if we just spray the request randomly across the web servers at the top, because a user's request might come in on one subset one time, miss to the databases, populate cache, and then the next time it comes in on a different set of web servers, and we have to repopulate cache again. So that's actually, this problem is minimized with a layer that's above what I actually drew on the board, which is we pin users to be sticky to a particular subset of web servers over reasonably long periods of time. And that makes it so that we get good cache utilization despite having subdivided our caches. So this still has some problems. We've distributed our read and our write logic, which means that it's harder to prevent thundering herds. And we have to deal with distributed write control logic, which is more complicated and more prone to latency problems. So we add another layer of cache. We call this the leader cache, which basically takes responsibility for coordinating the writes and updating the caches in the followers, and also for protecting the databases against thundering herds. We have some pieces of content on the site that are very popular. So how do we provide timeliness? So this is both, we want to distribute the writes out to everywhere as soon as possible, and also we want to provide read what you wrote consistency. So basically we get this by having a write-through cache instead of the way that Facebook used to be built with a look-aside cache. So by write-through, what I mean is the web servers talk to the follower sends the write to the leader sends the write to the database, and then as the commit messages come back, we can update the values in cache in place. So now we have to fix the cache contents in the followers. And we have a couple options here. So with objects, we just send out invalidation messages. We just say, if you have this in your cache, kick it out. Next time somebody accesses it, we'll pull it back in. This strategy doesn't actually work that well with association lists because the incremental cost of fixing the association list is a lot lower than the cost of reloading the whole thing later. Also, the benefit of having a complete association list is that it allows us to serve both positive and negative queries. So for example, we can definitively say that Z is not in the list of X, A, B, and C. But if we put a question mark in that list, then we'll no longer be able to answer the negative query. To try to preserve these values in cache if they're already there, we send out refill messages for association lists. We say, this particular part of your list is stale, please reload it right now. And then that causes a read to refill or to update the cache contents. You might ask why we don't just send the new value there instead of telling the other end that they need to ask back. And there's two reasons for this. So it's a space optimization because you don't have to send the data for the cases when the value is not actually in cache. But the most important reason is that it makes all of our cache consistency messages idempotent. And this gives us a lot of flexibility, especially in the multi-data center case where we don't have to guarantee that the cache consistency messages are delivered only once or in the correct order. If we have some sort of a failure, we can just replay cache consistency messages to get ourselves back to a good state. So the case when we have multiple data centers is pretty similar. No matter where the write comes in, whether it's in a replicate data center or the master data center, we forward it to the master region's leader cache. And then whatever the write path is, that write path will be updated synchronously, and the rest of things will be updated by asynchronous delivery of the cache consistency messages. In order to preserve the property that we always do our reads from the local data center, we delay the invalidation and refill messages for replica data centers until after that database has been updated. So we're actually using MySQL asynchronous replication to keep the databases in sync here. And we embed the invalidation and refill messages in the SQL. There's just a black hole table that we have specially formatted values in it. This is pretty similar to the way that we do invalidation for memcache. This means that after the replication occurs, then we can deliver the invalidates in the local cluster. So our last goal was high read availability, and we provide this by having basically at every step in the process of doing a read, we have multiple places that we can go to find the data. So, for example, if we're reading from a web server and we're unable to talk to the correct machine in our follower cache, we can send that request instead to a different follower. So this is an important failover strategy for us because it means that the cost of a failover read is basically the same as the cost of a normal read. Like we're talking to a machine that is supposed to be caching the data, that will cache the request. There's no extra cache consistency messages required in order to maintain consistency in the case of read failover at this level. And it helps us avoid metastable states where if we have failures because we're out of capacity and then that means that the failure path is more expensive, we might be in a metastable state where we never have the opportunity to catch up. If we can't talk to a leader cache, then we just bypass and go directly to the database. And the reason we're allowed to do this is because we've delayed the cache consistency messages until after the local database has been brought up to date. So we know that by fetching this value, we're eventually going to be brought, like even if the value that's in the database is older than the one that's in the leader cache, we'll still be brought up to date. So we also have one more failover path that we can handle, which is if we can't talk to a replica database, then we can proxy the request cross-country or cross-Atlantic to the master region and do the read there. This isn't something that we like to do very often because it's high latency, but it's important for our ability to be able to do database maintenance. So we can take a database down, promote one of the replicas to be a master, and then continue to run the site. And as long as we don't do that for too many of our databases at once, everything stays fine. So to summarize, and I seem to have had a little bit of extra coffee this morning because I got here sooner than I thought I would. We achieve efficiency at scale by separating the different layers and by having graph-specific caching that we can do updates in place. And then in order to scale to the size of data centers, we subdivide to optimize our network usage inside the data centers. We get write timeliness by doing write-through caching and then asynchronous replication. So the fact that we use a write-through cache gives us, except in some failover cases, gives us read after write consistency. And then we get good read availability by having alternate data sources. So there's a bunch of stuff in the paper that I hope you'll go look at. The time values that we use on edges also help us improve our cache hit rate. And we have more details about like our write failure recovery and write scenarios and stuff like that. So at this point, I'd like to open it up for any questions.
Gunsera, Cornell University. So this is a very exciting system, very nice talk. One thing I noticed, of course, is that the back end is MySQL padded with a whole bunch of caching to make it perform. Why would you not use a graph-structured database, given that the data that you're storing is indeed naturally and inherently of graph form? Or maybe put another way, if you could redo every aspect of this design, what would you redo?
So the first question is like why MySQL? And the answer is we're not wedded to MySQL, but having a generic backend actually it lets us focus the TAO system on just what we want to focus on. Like, so for example, MySQL comes with a backup system that we already have operational experience with and we trust, like it's not going to lose data. It also means that when we want to do accesses that don't fit the model that we've implemented in cache, like if we want to do a bulk data migration or a bulk upgrade, we can basically just code that directly as SQL. And you can think of it as the buffer cache in SQL is optimized for doing those types of large scrapes or whatever, and then the separate cache that we have is optimized for the locality of the graph operations that we want. And we kind of get the best of both worlds by having the two layers. That said, if there was a backend that was more efficient, we would be fine switching to it. And we could, because we actually have a clean separation between what the users, or what the web servers access and how we actually store the data.
Great, thank you.
Hi, I'm Michaela Blott from Xilinx Research. Thanks very much for your talk. That was really interesting. Can you give us an idea of the size of the nodes that you're storing in your caches?
So the nodes range in size. So I have the graph is in the paper. I don't have it specifically here. The largest nodes are 1 megabyte. Like most of the things in our graph, there tend to be many more of the small ones, but then there's a long tail of really large values.
Like for the pictures?
Yeah, well, so we're not actually storing the contents of the picture here. We're just storing a link. We have a thing called, we have a data store that's optimized for photos that we use to actually store the contents of the photo. So this is more like a pointer to it that is associated with all of that contains the metadata and the access control data.
Okay, so which items do consume 1 megabyte of data then? Out of curiosity.
Well, I run the system, so I don't look at the things. The last one that I saw that was actually really big was somebody that was encoding, there was 17,000 lines of pretty prudent JSON from PHP that it was being accessed several 100,000 times a second. So this is actually an interesting point, which is the TAO system generally works, and so every time it works, people kind of stretch it to the limits of what is possible, which means that the boundary of kind of how much data we store in it or how frequently we access it keeps, as soon as we get competent on a particular range of things, then people start pushing out. So we have meta objects in there that are accessed millions of times a second, for example. There's an iPhone application node that if we can't serve it, then you can't use the iPhone.
Okay, thanks very much.
Hi, Scholt. Oh, sorry.
Oh,
Scholt van ETH Zurich. I was wondering. Sorry, am I too loud? So I was wondering, this leader node, leader cache, it has to kind of contain the whole aggregated data which is in the other caches, right? I mean, this is what I gathered from your talk. So if that's not, maybe you can clarify that a little bit.
So the amount of memory, the bulk of our cache memory is in the followers, not in the leaders. The leaders don't have a very good cache hit rate on their own.
Okay, so they actually on the miss, then the followers go directly to this was something
they go to the leader. But the leader, so the followers can hold data typically for like a day or more, whereas the leaders might have an eviction age of like half an hour to an hour.
Okay, so you use it as a kind of just as a transport from you evict data sooner from the leader than.
What the main thing that the leaders do for the read path is not so much reducing our overall read request rate, but reducing the temperature of the hotspots.
Okay.
So if we have a particular thing that is being accessed a lot, then the leaders help reduce that.
Oh, I understand. Okay, thank you.
Hi, very exciting talk. I'm a musician from OSU. Actually, the workload you use is like only a pure read workload. But there's another talk from Facebook in the extremely large database in Stanford, just maybe a couple months earlier. They said, I'm not sure if you in the talk, but they said the system they're working with is like contains 45% of writes in the system, in the whole hybrid heuristic system. So how do you handle that? Well, I think in a write-intensive system, the write timeline is and the copy through cache will fail the performance.
TAO is not designed to deal with a write-heavy workload. Like we have similar systems that store nodes and edges without storing them, without backing into the database that are write-heavy, and we also have. You can basically consider this kind of the rendering side copy of the social graph. We also have versions that are there for less timely but more data-intensive analysis, like the things that try to figure out like who to suggest friends for or something like that. Like we're not running those out of this graph. This is for rendering the site.
Thank you.
Hi, Ayush Dubey, Cornell University. So TAO currently uses an eventual consistency model, which serves the Facebook use case well because you have a constrained API. You can just get nodes in edge lists. But if you were to expand the API, like you just mentioned, you have other kinds of systems for graph processing. What kind of consistency model do you think would be useful in that case?
Well, I should clarify that TAO actually we talk a little bit more about it in the paper, but because we're running the databases essentially at a higher consistency level, or the master database is completely consistent, TAO actually provides the opportunity, like we provide a flag that you can set on a query that lets you do it in a consistent fashion, albeit much more expensive than a normal query for those particular use cases. The requests that we get most often from the product engineers at Facebook, like how to expand the TAO API, it isn't about read consistency, it's about the failure semantics on writes. So right now we don't provide, if you write n things, there's about 2 to the n possible states that we'll end up in. And that makes life hard for them. So what they would like is a failure atomicity or kind of a stronger guarantees to simplify their life for if there's a failure.
Okay, thanks.
Quick question. Do you have problem with the deep traversal in your graphs? We're in a case where you need to hop multiple nodes to get to the end of your search query, or?
Well, we do those typically in multiple rounds. So the philosophy we have there is that TAO is essentially provides a very deterministic performance model. Like it's difficult to execute a query in TAO that is expensive but returns a small result. If you find yourself writing PHP code that has a big for loop around doing a bunch of TAO queries, it's pretty obvious that that's going to be an expensive thing, and you only are going to do that if you want to. And then we also have other systems that do more sophisticated indexing of much smaller subsets of the graph. Like you wouldn't use TAO to figure out whose birthday, which of your friends has a birthday today, for example. We have a system that indexes that in a reverse fashion.
All right, let's thank the speaker.